Hello everyone. The last lecture we've been discussing coupled oscillations with a number of masses. Today we're gonna increase the number of masses and talk about the general case of n-coupled masses. So we have a string here and there are masses on the string. The string is fixed at this boundary. We call this the boundary condition. So the string cannot move at that point. And the masses are at a constant distances from each other. And we have n masses, and the string is also fixed on this side. And we want to know what are the natural mode solutions for this system. Now we make a few assumptions. The first assumption is that the movement is small, okay, and there is no movement in the x direction. All the movement is in the y direction, and in the x direction the movement can be negligible. So I can write these assumptions down. Motion in the x direction is negligible. There you are. Okay, and the amplitude are small amplitudes. And this means that there is no change in tension. The upper assumptions allows us to concentrate in the y direction only, so we neglect the motion in the x direction. And the second assumption allows us to assume that there is no tension in the string. Okay, so we at some moment in time we can find this being here, this one maybe here, this one maybe here, and so on. So in general, we want to look at some mass from P. Let's see that at some time it's found here, and this mass is found here, and this one is here. We have T here and here. The height here is y of p minus 1. This is the point p minus 1. The height here is yp. And here is yp plus 1. Right? Now we look at the angles. So this would be up here. This would be alpha p minus 1. And this angle here is alpha p. Now I can write the Newton's second law for the object at point P. That m y double dot equals, what do we have? We have t sine alpha p minus 1 in that direction, and t sine alpha p in the upper direction. Y is defined positive upwards, so I can write minus t times sine alpha p minus 1 plus t times sine alpha p, that's it, point p. What is this? What is the sine alpha p minus 1? Sine alpha p minus 1 I can calculate from this and this. What I didn't mention is the length. I said it's equal between every two adjacent masses. I didn't give it, so we can just give it L. So the length is L. The length here is L because the movements are small. So the length is there's no tension, right? So let's see, what do we have? We have a sine, this divided by this, and this is, let's start with this one, so minus t, sine alpha p minus 1, so it's yp minus 1, divided by t, divided by the length. So we have yp minus 1 divided by L, and the other one is t times, this is yp plus 1 minus yp, and divided by L. So we have yp plus 1 minus yp divided by L. You can define omega 0 squared as t over ml, makes things simpler. So we can write now so now we have y double dot, it's at point P, so I should write P here also, right? This is at point P, so add the divide by the mass. You see this? Yeah. I divide by the mass, I get T over ml, and that is omega 0 squared. So I can already write down here plus. I have one yp here and another yp here with the same sign, which is a minus sign. I take it to the other side, so I have 2 omega 0 squared yp, and we have a yp minus 1 and yp plus 1. The first one would be with a plus sign and the other one would be with a minus sign. So you can write minus omega 0 squared yp plus 1 minus yp and let's check that. This one would be plus and this one is plus, so both of them are in the same sign. Yeah, both at point p plus 1 and at point p minus 1. And this is equal to 0. Now we have to do this for every single object and then write all the equations, or the n equations that we have. Let's start with two objects. So at y0, we know that there is no movement, right? This is it's fixed. So y0 is always 0, and yn plus 1 also is also 0. These are the boundary conditions. For n equals 2, you should already have a feeling of the natural modes. The lowest mode, they would move in phase, so they would go up and down in phase like that. And for the other mode, they would be out of phase, so it goes something like this. So what you would expect to see is at the lowest mode, they would go like this in phase, and the other mode would be something like this, out of phase. This is omega minus, and this is omega plus. Okay, so let's solve for the case of n equals 2. Let's write down, so y double dot 1 equals a plus. We should have two equations now, right? Plus 2 omega 0 squared y1 minus omega 0 squared at y2 plus y0 equals 0. We know this is 0, but I'm going to keep it there for a minute. And for the second object is y2 plus 2 omega 0 squared y2 minus omega 0 squared y3 plus y1. Use a trial function. You take yp equals some amplitude ap cosine omega t. You substitute this back there. The second derivative, that will give us minus omega squared a1 plus 2 omega 0 squared a1 minus omega 0 squared a2 plus a0. Same thing. What is the amplitude at point 0 is 0. It's fixed at that point. And this is equal 0. These are the two equations. And for the second equation, minus omega squared a2 plus 2 omega 0 squared a2 minus omega 0 squared a3 plus a1. And a3 here is 0, right? Because it's the other side. So it's y3 here. Alright. The reason I left these here is because I wanted to show you, so I didn't put 0 here and here. This should be 0. This should be 0. Because in general then you can write also for the minus omega squared AP plus 2 omega 0 squared AP minus omega 0 squared AP plus 1 plus AP minus 1 equals 0. That would be the general equation for any point P. Now we're going to make a shortcut. By using what you've learned so far, I want you to think about if you had so many objects and infinite number of masses, and you just think about the lowest mode. They all should be in phase, right? So if they all should be in phase, you would expect them to do something like this. These are the entities, then you would expect them to do something like this. You also know the highest mode also, that every two neighboring objects would be out of phase. So that's going to be something which is, one is up, the other is down, one is up, the other is down. I'm not going to put this here. But what do you think would happen in the second mode? The second mode, you would expect that half of them would go up, while half of them would be out of phase with the first half. And when the second half goes up, the first half goes down. So you expect, so this is in the first mode. This is n equals 1. It would do something like this. Right? Up and down, up and down. This is y, this is x. And these are fixed. And for n equals 2, it would be something like this maybe. The half okay, so this would be n equals 2. So we need to look at a function that is able to give us this kind of description. So we want it at the first point and at the last point to give us 0. We're looking for an amplitude function. So some AP, but the general one for any point, so AP n, so the first point we want it to be 0, and the last point we want it to be 0. This looks like a sine, right? So if we choose the following, some amplitude, sine the point number, so P times n pi over n plus 1. Okay, let's just try this function and see if it satisfies what we have here. It's a sine, so it has that shape, but we want to make sure that it's 0 here and it's 0 there, right? And we can see that at point n plus 1, so when P is at n plus 1, at this point, we get sine n pi. That's a 0. When P is at the first point here, which is 0, then we get also sine 0, which is 0. So this function seems to be satisfying what we have. And this is for the first mode. N would be the number of modes. Now if we look at the second mode, for example, let's see. Second mode, we'll have a 2 pi here. If I have 0, so that point is always 0, that's fine. And if I have n plus 1, I get 2 pi, so sine 2 pi, again, is 0. So also for the second one, this works. What happens, for example, in the middle here? At the middle here, you would get, so this is 2 pi, right? And here you have n over 2. This would be n over 2, and you get, what do you get? You get pi instead of 2 pi, right? So again, this would be 0 for this case. All right. let's just now type for what we have there. For the example, when n is equal 1, AP1 equals C1 sine P times pi over n plus 1. This is for the first mode. And for the second mode, we have AP2 C2 sine 2p pi n plus 1. And then this is general, right? But we can also use it for the example here. If we use it for the example here, then we know that, for example, n is 2, right? Let's substitute, and the big N is 2. And small n also, we have two modes, so we can look at either this one or this one. And p can be 1 or 2, or 0 or n plus 1 as well, right? Because you can also consider the fixed parts here and here. So it would be 0, 1, 2, and 3 in this case. Alright, so what is this, the frequency, omega n? We want to find the natural frequencies, right, and the normal mode frequency, omega 1, omega 2, omega 3, and so on. I'll do it on the other screen. Okay, so what is omega n? This is pure trigonometry now, which you can find the details in the book, French. AP minus 1 divided by AP. That would be twice cosine the angle. This is minus omega n squared plus 2 omega 0 squared divided by omega 0 squared. This is 2 cosine n pi over n plus 1. So omega n squared is 2 omega 0 squared 1 minus cosine n pi n plus 1, which is 4 omega 0 squared sine squared of n pi n plus 1. Okay, so we can write for omega n and yn. So omega n is 2 omega 0 sine n pi over n plus 1, and y of Pn is at the normal mode, so all of them would have the same omega, right? So if you want to find the displacement of each of these, then that would be y Pn, so it's a Pn cosine omega nt. Okay, so now I'm going to make a demonstration. I have a rope here. So you can think about it as a continuous medium of coupled masses together. There's a large number of natural modes here. I'm going to generate a disturbance. Normally, one of the students will give me a hand in this demonstration. Now I need to use the door handle. Okay, I want you to look closely, how much you see from this. see this. Okay, 3, 2, 1, go. And do it one more time. And go. Oh, okay, that was a sign. So the disturbance looks like it's moving in that direction. I hope you've seen a mountain moving from that direction going there. We're going to discuss that later on, but if you also noticed carefully, then there was a disturbance coming back, and when the disturbance came back, that wasn't a mountain anymore. So let's analyze the situation. All right. So let's start with the small element of the rope. This is the element. The point X. This is X, and this is at X plus some delta X. This is the Y direction. The angle here is theta, and the angle here is theta plus delta theta. There is a tension T here and tension T here. And the distance would be, this is dx and dy. Okay, now we don't have a specific mass at a specific location because it's continuous, but we can talk about mass per unit length. So if I know the length of this element and I know the mass per unit length of the rope, then I just multiply the length by the mass per unit length. So mu is the mass per unit length. And this small element has a mass dm. That would be mass per unit length times the length, which is dx. Alright, the force is in the y direction. We have the same assumptions as before, so we're neglecting any movement in the x direction. The mass is moving in the y direction and not in the x direction. The disturbance looks like it's moving in the x direction, but the physical mass is moving in the y direction. So the force is in the y direction, and that is minus t times sine theta plus t times sine theta plus delta theta. Yeah? From this side we have t times sine theta is in this direction, right? And here we have it in the upwards direction. Small angle approximation, and we can just write t delta theta. So F equals ma, m is dm times y double dot and that is T delta theta. The dm is mu dx, so mu dx y double dot equals T delta theta. What is tangent theta? Tangent theta is dy over dx. Tangent theta is dy over dx. The small angle approximation, so theta is dy over dx. But what is the derivative of tangent theta? So the derivative with respect to x, so d dx is 1 over cosine squared theta. So now I can write 1 over cosine squared theta, a small angle approximation, that would be 1, right? So d theta dx, d theta dx would be given by, this is also d squared y dx squared, right? This is the derivative of tangent theta, so that gives d squared y over dx squared. So d theta dx can be approximated by d squared y dx squared. Need to now use partial derivative, so d theta dx equals d square y dx squared. So coming back to our equation, we have mu. What do we have here? This should have been delta x. Please correct that. This should be delta x. Yeah, this is. So we have mu delta x dy, the second derivative in time, equals t times delta x, the second derivative of y dx squared. See it from here. So delta theta is delta x dy dx squared. All right, now I'm doing something that I shouldn't really do, but I'm gonna cancel out this delta x with this delta x. And what I get is the following. The second derivative of y with respect to time, mu over t, equals the second derivative of y with respect to space. I ask, what is a possible solution of this equation? What is a possible solution for this equation? Any single valued function f of x plus or minus some constant c times t would satisfy this equation. You can try that yourselves. and see if that is satisfied or not. And see here the constant is the square root of t over mu. Choose any function which is single valued, any function of x plus or minus ct, and it would satisfy this equation. What are the dimensions of this constant c? If you know the answer, please type that in the chat now. You see, this is position and this is time, so this has to be velocity. So now we can write replace that constant c with a velocity v. So we can write v equals square root of t over mu. And we have 1 over v squared d squared y dt squared equals d squared y dx squared. This is known as the wave equation. This velocity here describes that moving disturbance. So it's the velocity of the moving disturbance. Let's see if it makes sense first that this is the velocity. This is the tension up here, and this tells me that if my rope has a higher tension, the velocity should be higher, the velocity of the disturbance should be higher. And that feels right. If it would be really, really tight and you try to make that disturbance would move faster. And if it's not that tight, so t goes down, then you would expect it to travel slower. And here I have the mass per unit length. This tells me that the higher the mass of the rope is, the slower the disturbance would travel, and that also makes sense. So this is quite intuitive. Now I'm going to ask you another question. So please type that in the chat. I mentioned that any function with x plus or minus, now I can write vt, would satisfy the any single valued function would satisfy the wave equation. And my first question to you is that if I have a disturbance, and this is the disturbance, I want it to move, let's say that this disturbance is moving from left to right. So after some time, you find it here. Okay, this is at time t0, and the disturbance is traveling from left to right. And the question is, how do I describe it now? Is it going to be x plus vt or x minus vt? If you think it's going to be a plus, just type plus. If you think it's going to be minus, just type minus. Alright? If the disturbance is traveling from left to right, then you should have a minus here. And if the disturbance is traveling to the left, then this should be plus here, giving that this is the increasing value of x. All right. Now the question, and for that I'm going to redo the demonstration. Alright, so I'm going to generate a mountain, and I want you to look at how it comes back. I hope it is somehow clear. If not, I'm going to play a video shortly. Alright, for me at least from here it's not so clear. I'm going to try to generate a valley now and see how it comes back. Now this was a bit clear, so I'm generating a valley, so it goes down like this in that direction, and it returns as a mountain. Oops, did not return now. Let's try again. And again. It's harder to generate a valley than a mountain. Here we go. That was not bad, I think. Alright. Probably I'm gonna show you a video to see that clearly. Okay, so what's happening here really? What's happening? Why is it that when we send a mountain, and remember it is fixed on the other side there, why does it come as a valley? And when we send the valley, it comes back as a mountain. So this is the case. It's fixed here. I send a mountain like that, and it comes back as a valley. We want to understand qualitatively why this is happening, and in the next lecture we're going to derive that as well. Let's look at this point, at the fixed point here. This is a fixed point. This fixed point means that the amplitude there is 0. At this point the amplitude is 0. So let me put it this way now. As the mountain is arriving here, at any point that it comes here, we should generate an opposite wave that cancels out that amplitude. So we should expect to generate exactly opposite wave at the exact opposite direction. So for example, if we are at some time here, where this is supposed to be like this, if it wasn't fixed there, if it was longer, then you would have the wave on the other side. The only way to for the system to be able to digest what's happening here is that this amplitude has to be cancelled by generating another wave at that point with exactly the same amplitude. So now you've basically superposing two waves together, and the superposed amplitude is exactly 0 at that point. But this happens at every point here as it moves, okay? And that's why you would have generated an exactly opposite wave with the same amplitude. And for the same reason, if you start with with a valley as it goes to that point. At that point it can't be with an amplitude, it has to be 0, so it has to be cancelled at every point along the valley. So at this point, for example, you have to generate amplitude as high as that, and at this point you have to generate amplitude as high as this much, and so on. And therefore, basically, what you're generating is a second wave, which is superposed at that point, giving you a 0 amplitude. But that wave now is traveling in the opposite direction, and it has exactly the opposite amplitude. So a mountain returns as a valley, and a valley returns as a mountain. Now what happens if instead of this fixed end, if we allowed a free movement? So imagine if we had some column here maybe. This is the rope, and this is tied around it, and it can freely go up and down. It's no problem, right? Because now the wave, as it goes there, it wants to be at this amplitude at this point, and that's not a problem. So at that point, what happens is that this whole thing will go up. So you would see the whole thing raising up and down. For that reason, you would expect, in this case, the mountain returns also as mountain, and the valley returns as a valley. Alright, that's it for today. I'm going to show you a few videos now to see this clearly. Until next time.